Yes. The goal is to speak a bit about braid groups. It's nice because there are several different definitions of them. So we will speak about different flavors of mathematics. The problem is that there are too many things about them. So of course I won't be able to speak about everything. And in particular, if I want to say a few different things, I won't be able to do all the proof, and certainly not the proof like Patrick explained, to explain everything. So there will be a mixture between proof that I will do and things I will ask you to accept so that we can do a bit more things. Do not hesitate to ask questions, and we can go back, or I can give you references, or maybe I will post notes, something. So there is a lot of material on the web about them. So if you want to learn more, you will find a lot of things. A very complete reference is a book by Kassel and Turayev. Called Braid Groups. I couldn't find a physical book in the library, but there is like an online book available, so you can find it if you want. But there are many more references depending on what you want to do with them that are relevant. And first, and at the difference with the book, I want to start with something which is more geometric braids, because I think it mimics more what we think about braids in real life. So if I want to do a braid in real life, so my standard thing that I do on my hair, maybe something more fun with more strands here, like that. So what's happening? I have strands, so here I have 6 of them. And what are these strands? Well, they look like some segment, so like 0, 1. So to describe geometric braids, we'll get in 3D somehow. We'll get a certain number of these intervals, 0, 1, and we'll explain how they move in 3D. So let's start. What I will call the geometric braid. On n strings is a set. So it will be a subset of R2 times 0, 1, and somehow 0, 1 will be this vertical direction and the length of my braid. So a set B consisting in n interval. So if I want to be precise, I'm in topological intervals. So they are called the strings of B. No, round B. Such that so I really want my string to not get knotted on itself. Otherwise, I won't be able to do my hair very well afterwards in the evening. I don't want this to be knotted on another one as well. So one way to encode this is to ask that the projection so this is I equals 0, 1. And my R2 will be planes like that, horizontal ones. How did I orient this? Yes. X, Y for R2. So my projection from R2 to 0, 1 into 0, 1. And I mean by that, if I take coordinate x, y, t, I send it to t. Restricts to each string, so each interval 0, 1, that are my pieces of braids. Each string S as a homeomorphism so from the string to 0, 1 onto its image. So I will try to draw something in 3D. X, Y, 0, 1. So maybe something like this. Just that I have maybe going here, maybe another string here, maybe both going in here. And maybe passing here. So I want my projection in that direction to be a homeomorphism, so on the strings. So if I forget one of all my strings but one, let's look what the purple does. That's that. And the blue one would do something like that. Homeomorphism. Everybody remember what I mean by that? So I want the projection restricted to S to be continuous, a bijection, and the reverse bijection to be continuous as well. So I really want to identify these strings with the interval 0, 1 through this projection. Another thing that I want, except that this is fixed, so maybe I'll start there. Another thing that I want this to be prescribed. And what I mean by this is like the upper extremities and the downstairs extremities. So, and because I'm in between 0, 1, and I'm in R2, I can actually decide for my definition where they should be. So I'll continue on this one. And I'll list it again if I need to. So, such that also so my intersection with the upper plane, I will decide that they should be So for y equals 0, and I will decide there with the abscissa 1, 2, 3, till n. So the intersection with the upper plane will be 1, 0, 0, 2, 0, 0, till n 0, 0. And I want to prescribe also the downstairs intersection. So 1, 0, 1, 2, 0, 1, and 0, 1. All right. So what you... Let me draw again a picture. So I don't remember how it was. Something like this. No, the other way around. Etc. I had green in the bottom, and yes, you are going here. Should go further here. Keep it for now. Doesn't matter really. But what you see is that if you're scanning your space with horizontal planes, which I will call PT, at each level T, your braid intersect at exactly n distinct points. So if PT is the plane R2 times T, each strand meets PT at exactly 1 point. And so this is in particular true at 0 and 1. So if you start at t equals 0 and you follow the same strand, you will end up so starting at, let's say, a certain I00 and following the strand, passing by this point, then we end up at t equal 1 at, did I give a name? Maybe I should not give this name. Some s of I, which is between 1 and n, 0, 1. So what I did is that given a braid B, I defined a map from 1 to n into 1 to n and to I. I associate S of I. And do you guess what kind of map this might be? You know that to each strand, so for each I, you have a unique S of I associated to it. So it's a bijection from one end to one end. So it's a permutation. So this way, you associate it to any braid is associated a permutation, let's say SB, from the permutation group. Whether the map is surjective, well, I leave you this as a question. But we'll answer this later. So, where are we? From our idea of how a braid looked like in 3D, we gave a definition in a geometric way with topological interval that are allowed to move in 3D, but with some prescribed conditions so that we don't get some knotting, etc. And some prescribed model because we decided where they should hit the plane at 0 and the plane at 1. Now the mini course is about braid groups, so they should be a product. So we want to define a product on these braids. And well, if I give you one braid and I give you another braid, how can I make a product out of two of them? Well, I can simply start with one and just continue with the other one. So let's see if this defines for us a product. So where do we go? Up. So are there questions? Also, you can ask them in French if you don't want to ask them in English. So I start with two braids. So B1, B2. B2 geometric braids. So their product. So I could define the product to be taking the braid between 0 and 1. Let's say the one corresponding to B1, and then stacking underneath the braid between 0 and 1 for B2. But from my definition, I need them to be between 0 and 1. And if I just do that, they will be between 0 and 2. Right? 0, 1, and 0, 1. So what we do is that we reparameterize, so we make it kind of smaller in that direction, or you can say that you go through the strand faster, so that we put B1 between 0 and 1/2, and then B2 between 1/2 and 1. So that's the idea of the product. Nothing crazy there once you have this idea of stacking. So their product, B1, B2, is defined as the set of points x, y, t in R2 times 0, 1, such that what? X, y, 2t, so 2 times faster through t, is in B1 for t between 0 and 1/2. So when I reach 1/2, 2t reach 1. And x, y, 2t minus 1 belongs to B2 for 1/2 t 1. So when I start at 1/2, I'm at 0 for 2t minus 1. When I end up for t equal 1, 2t minus 1 is at 1, and I went through the full B2. So in picture, if we want, let's see, my old one. Should keep the one that I had ready on my paper first. Oops. This one, so that I keep it till the end. So this would be B1. This would be B2. Let's see. I draw this. I draw that. No, should be closer. And see if I need to have a precise picture later on or not. Up. And if you're on a paper with lines, it's easier to keep the 1, 2, 3, 4, 1, 2, 3, 4 on the line. So this would be B2. And now I want to shrink them and to stack them one above the other. So this is 1/2. So up. Up. Green. Should do this. So I have less space to draw them, but it's still okay. Yep. If I keep those. It's easier on a computer, you can do copy-paste of stuff. more or less. So because B1 and B2 had the property of geometrical braids, and you just can see how they get together into one interval, what I defined here, B1, B2, is a geometric braid. You can write details if you're not convinced. Now I want a braid group. So what do I need to get for this product? Remember your algebra course. Yes? Can you say it louder? Associativity. What else? Yes? A neutral element, an identity element. And an inverse or a symmetric element for this product. So, I don't know. So we need associativity, an identity element, and each element has an inverse. Is this product that I just defined associative? What do you think? Should we vote? So for associativity, I need 3 braids. So I need B1, B2, B3, 3 braids. And I need to check that if I do first the product of B1 and B2, and then B3, it's the same as doing the product of B2 and B3, and B1. So if I look at my definition, I'm taking my box of B1, my box of B2, my box of B3, between 0, 1, 0, 1, 0, 1. For this product, I will first do this one. So between 0 and 1/2, I put B1. Between 1/2 and 1, I put B2. And then I want to do this bigger product. So I want to put this 0, 1 into 1/2. And then a box of height 1/2 for B3. So this is B1, B2. B1, B2, B3. I will have B1, B2 here, between 0 and 1/2. So I have 1/4 here, and 1/2 and 1, B3. And on the other side, well, I will be doing first B through B3, and then I will put them in a box of size 1/2. And here I will have B1. So you can take your favorite braid. It's taking me too much time to draw them all. So maybe just simple ones. B2. Oops. And B3. Just to fix the idea. Oh. So what do I get? I get something small. Oh. Green. B2. I forgot to put this one. And what did I decide? Underneath? Underneath. Up. So this would be it. And now B1. So I have a bigger B1. And then small, very small. What did I do? Did I miss something? Yes, I missed something. So this is big. This is smaller. And this should be smaller as well. Again, if you have a paper with lines, it's easier. Are they the same as sets? Yes, no? No. So, no associativity. A bit annoying. What could I do to allow associativity? Say it again out loud. Yeah, we could. And what there was upstairs? Some hands? No? Yes? The same? They will have the same permutation, yes. So, but we need something more refined at that. So we need to allow the strands to move, which goes to this idea of homeomorphism. So if I'm getting back to my real life ones, there was another issue that we didn't speak about yet. You see, if I'm trying to braid my hair, I'm doing this and then that, it's really just the same as having the same, just two strands lying straight. Because this won't hold, it will just unbraid. And so we don't want this to be different than the braid that is straight. And the same way for this product, we want the strands to be allowed to move a bit continuously. So what we will do is that the geometrical braid, we won't look at them just as set, we will look at them up to deformation, continuous deformation. So we will define an equivalence relation given by this deformation, and the braids that we want to see for the braid group is the quotient set by this equivalence relation. But it's very natural, it's not something that is completely abstract crazy. So, no, just this one. So, to fix this, look at braids, geometric braids. Up to continuous deformation. And so the right notion for this will be isotopy. So let me define this property. So two braids, two geometric braids, B and B prime, are isotopic. If there is a continuous map capital F from B times 0, 1 to R2 times 0, 1, such that so this, I'm saying up to deformation. So I will want a family of braids going from one, which is B, to the other B prime. And so this big map will encode all these deformations. So you want that for each variable S, which lives in this parameter space 0, 1. So it's a new 0, 1, not the vertical one. So you have a map Fs that consists of restricting your map capital F for the variable S equal, well, S. So it goes now from B to R2 times 0, 1. And to an element, well, X or XYT, capital X. So I fix S, and this should be an embedding so again, no, I finish the sentence. Is an embedding the image of which is a geometric braid. So I want two geometric braid B and B prime on n strings. So I keep the same numbers. And this is a geometric braid on n string. And so what does it mean embedding here? So you have the source B. You have the image, which I will denote B sub S. It should be a bijection. It should be continuous. With the inverse continuous. But this makes only sense once I restrict my image. Well, where I restrict the target to my image to take the inverse. So I really want this map to allow me to identify B and BS. And my image should be also a geometric braid then. So this suppose T3. So this is one condition to get this continuous deformation. And then the two other conditions are about the fact that I want this to be an isotopy between B and B prime. So I should say that I start at B and that I end up at B prime. And that's easy to do. I just ask so I just ask my F0 to be the identity of the braid B, and my F1 to be that its image that I denoted before BS, so B1 here, is B prime. So the map F, or this family Fs of B, they are both called the isotopy, or A isotopy. So I'm always wrong with the prepositions of B into B prime. But I will often say from B to B prime or something like that. Right. The fact that F is continuous and your endpoints are discrete, this implies that your geometric braids are always keep the endpoints. So B and B prime and all the Fs of B have the same endpoints because of that. So F continues plus set of endpoints discrete. Fs is the identity on the endpoints of B, which is morally what I want. I want to keep my same braid, but I just want this to be allowed to move a bit in between. This is my deformation. All right, so, and I claim that this B is isotopic to B prime. Is an equivalence relation. So let's wake up from our definition a bit more. So, well, yeah. B isotopic to B prime is an equivalence relation. What do I have to check? Yes. So, reflexive, symmetric, transitive. Reflexive, what does it mean? So I want for any braid B to be isotopic to itself. Is that true? So which identity? Well, just not at a set, but yeah, I'd be. Did you say I'd be? Identity of B? Well, or something like that. So you really want this map to be just X gives you X. All right, symmetric. What does it mean? Yes. So you would take F minus 1. Uh-huh. Are you sure? So maybe it works. I was not thinking about this one. So if I take Fs minus 1, I go from Bs to B. So you need to do something else, because you need this to start at B prime. So I don't know, maybe you have an idea? So yeah, that would be my standard idea to get. So what you have to think about is this family of deformation. So schematically, I start at B, and it's very schematic. I want to end at B prime, and I have this continuous family from B to B prime. So from B to B, I just can have the same family. From B prime to B, my idea would be to go the other way around, so to go with the time in S in the opposite direction. So I would take 1 minus S. So let's see how this would work. If I take the map so f of x 1 minus s. So for s equals 0, I have x1. So this belongs to B prime. For s equal 1, I have f of x0. So this belongs to B. My issue is that my f1 minus s is still defined from B into R2 times 0, 1. And I would like this to be defined from B prime. Do you have a fix for that? F1 before time the identity. So remember that your F1 identifies B and B prime. So you can go from B prime to B. Is that what you're trying to do? Taking the inverse map of F1, and then you can follow up with F1 minus S. So my suggestion for a homotopy F prime would be that F prime, let's say of S, would be defined from F prime to, R2 times 0, 1 by taking F1 minus 1 and then composing with F1 minus And then you should have the identity for s equals 0. You have b for s equal 1. And all should be checked. But you can do the details. All right, transitivity. So this is 1. 2. So what do I need to check for transitivity? What do I want to see? Right? That's what I want. How do I get it? So B is equivalent to B prime. So I have an isotopy F from B times 0, 1 to R2 times 0, 1. In other words, I have a family Fs of B. Here I have another isotopy. So from B prime to B second. And I want to build out of this an F second from B times 0, 1 to R2 times 0, 1. So this Fs of B at 1, it goes into B prime. This F prime at 1 goes to B second. And this one I want to go from B, so the identity at 0, and at 1 going to B second. Any idea how to achieve that? So again, we have this things that is moving between 0, 1, and what we would like to do is to follow this one, and then follow this one to go from B to B prime. So let's try to just follow one and then the other in a parametric way. So if I follow with S between 0 and 1 here, and then with S in 0 and 1, I will go through 0, 2 somehow. If you remember my schematic thing. Do I have thread somewhere? So I'll have B, I'll have B prime, B second. Here S will be between 0 and 1, S will be between 0 and 1, following F, F prime. So I could build just a map for S between 0 and 2, following this one and then this one, or I can reuse the trick that we had for the product. I can go faster here and then faster here so that I still live between 0 and 1. And I just fix my parametrization, and I will probably need to fix something here with B prime, just as we had to fix for the reflexivity. So do I have a formula for you? Maybe. So I claim that if you pick your f second to be f2s for s between 0 and 1/2, and then I will do again 2s minus 1 and redo the trick of taking f1 minus 1. No, f1 now. I want to go from B to B prime, so I just have to take f1 for s between 1/2 and 1. This should do. And this is exactly what I said I did. I'm following this family, this continuous family of braids between B and B prime, just faster, between 0 and 1/2. And then I follow the next one, but I remember I started at B prime, and so to start at B, I just compose with F1. And that defines for me an isotopy F second between B and B second, and indeed, I have an equivalence relation. And so now the braid I want to see, it is the geometric braid. Up to isotopy. So now my objects won't be this subset of R2 times 0, 1. It will be subsets of R2 times 0, 1 up to isotopy. And I claim that this fixes my problem of the product, all of it. So there was a problem with associativity, but there was also a problem with looking for inverse, etc., that we didn't check, but you can meditate on that. And once we work with isotopies, then all is fixed. So more complicated space because it's a quotient, but it fixes all the problem that we had for the product, so the trade is okay. So so I will call this Bn. On Bn, the product above defines a group structure. Can I just claim this? Should I check something? If I ask, it's probably yes. Yes? It's worse than that. No, it's worse than that. I have to check something before speaking of an inverse. Because, yes, I defined a product on geometric braids, and now I'm claiming that I define a product on the quotient, but I never told you that this product was well defined on the quotient. So what should I do? Say it out loud. Yes. So, yes. So to have an internal law for that, in this case, if I have B1 isotopic to B1 prime, B2 equivalent to B2 prime, I want to look at their product then in the quotient, But this only makes sense if the product of those two are the same, so that I can take any representative in my equivalence class to make the product. So, right. So now we have to take the subset defining B1, B1 prime, B2, B2 prime, take the isotopies that we have in between, take the product, and check that all that fits well together, if we want to check that. So, do I want to do this in detail? I'm not sure. Do you want me to? It's kind of similar to the picture we did already. So I have B1, B1 prime, B2, B2 prime. What names did I give? That may be a bit sketchy this time, but still. So did I give a name to this? I went too far away. Okay, proof. Sketchy. So because B1 is isotopic to B1 prime, I have a family Fs of B1 from B1 to B1 prime. Because B2 is isotopic to B2 prime, so maybe I will call this F1s. And there exists another family Fs2 of B2 from B2 to B2 prime. What's your guess for a family between B1, B2 to B1 prime, B2 prime, built out of this? I have a family of geometric braids between B1 and B1 prime, a family of geometric braids between B2 and B2 prime. So between their product. Yeah, so if you take it for the first part, this one and this one, what you're doing is you're taking the product of these two, simply. Each of these are geometrical braids, so taking their products makes sense. So is a continuous family of geometrical braids, geometric braids from B1, B2 to B1 prime, B2 prime. So it's a bit of a sketchy proof, because if you really want to write this as a map from B1, B2, etc., you probably have to fix a few maps and so on. So I leave the details for you, but this is the idea. So now we have an induced product on the quotient space. So now if I'm, oh, I denoted that Bn time Bn into Bn, I can take a braid represented by B1, a braid represented by B2, and I take the class of their product. And what we just check means that whatever the representative I take here, whatever the representative I take there, I get the same element here in the same class. So now I have this operation. And I can ask myself, well, is this now a group operation? So I can check associativity. Which I will not do. Actually, I will not do in detail all of this. But you remember the pictures we had? We had these braids between 0 and 1, 4, 1, 4, 1 half, 1 half 1 to compare with the same ones, but spread differently in the interval, 1 half, 1, 4, 1, 4. So really moving in a continuous family fixed this problem that we had for associativity on the geometric braids. So yes. Then we need an identity element. So we need something, let's call it E for now. E such that, so now I should be working with representative. So E such that B times E is E times B is B. And we didn't talk about a guess that we could have had for geometric braids, but what could there be? Suggestions? For FS, you mean isotopies. I would like a braid, a geometric braid. So identity is not far. You just want your B to be always the points 1, 0, 2, 0, etc. all the way down. So simply this guy. And indeed, if I take a braid and then I compose it with the thing that goes simply down without making any crossing, then, well, if I do, like, say, B is here, and my neutral element is here, so indeed it's the same as doing B, but maybe in more loose way, or maybe it's the same as doing B, just in the part between 1 half and 1, which would be these operations. So, no, downstairs. So this E is just the set one zero zero 10T 20T etc. And indeed, you can check that if you do B times E for any braid, it's the same. It's isotopic to doing E and then the braid, and it's the same as spreading the braid along your full interval. So this would be our identity element, and indeed, the problem of the inverse. How do I do an inverse in this braid group? Any guess? So if I have a braid and I want to get back the straight strands, what should I do? Yeah, somehow something like that, except that you have to be careful about the reflection that they don't. So yeah, horizontal is probably enough. So you want to debraid it exactly the same way you braided it somehow. So if I cross it here, I need to cross it again above. If I cross it here and then underneath, I need to first unbraid underneath and then above again. And where I'm going to is also to mention generators for this braid group. So for now, what we have is a product on a space which is associative and has a neutral element. So it is a monoid. It has a name. And I can give generators for a monoid. So where I want to go is that if I just look at crossings of two strands, this one, or the opposite one, this will generate for me this braid monoid for now. So as a monoid. And so generating means that I can write any element as words in these generators, and I will be able to express the inverse also nicely. So maybe a nice proof to, well, proof or guess where to find these. No, so this was what? What's the last one I did? Okay. But yes, the idea is to unbraid and to do something symmetrical, and we could also encode this like that. Super. So for now, we have proved that Bn is a monoid. And the claim is that Bn is generated by the following. So of course I keep talking about the geometric braids, but each time I'm just speaking about the isotopy class of them. But what I can draw or what I can speak about is like one of them, one of these representatives. So between 0 and 1, I like red. Where is red? So 1, 0, 0. Let me just write 2. N 1, 2, N. And in between I have I plus 1, I plus 1. So this guy, yes, is sigma I plus. I have the same one, but with the other crossing. So this one above, and this one below. And this will be sigma I minus. So what I'm secretly doing, since I'm trying to draw them on the board, and especially now, are braid diagrams. So there is like a full justification of those that I won't do. So what do? We take the projection, maybe another one. There was already a projection before. From R2 to 0, 1 to R2 times 0, 1. X, Y, T. So this is a remark. Goes to X, T. So I'm projecting in the Y direction, I'm collapsing it. Except that I do remember which one had the bigger Y. So here when I'm breaking this line, I'm explaining that this strand had the bigger Y. And here I'm explaining that this strand had the bigger Y between the two. And you can check, but this needs a bit more of geometry that we don't have time to explain today. That you can always, for any geometric braid, you can find in its family of isotopic braid, you can find a geometric braid that will have a projection like that that is nice. And what I mean by nice is that the crossing will look like that and never like that. And so, the other way around, you can write a diagram like that just on your sheet of paper on the board, and this gives you a geometrical braid because you can lift it up to Y. So there is some justifications to do to allow me to work only with these pictures instead of the geometric braids and just tell you that this defines for you one braid. But I think it's intuitive enough that you might agree that it's doable. It should be done. We don't have time, and I prefer talking about other stuff for braids than doing these proofs. I mean, a bit away from Bourbaki here. So, all right. So we're drawing this diagram, and they prescribe for us some braid in BN, or in isotopic class, because I'm allowed to move. So I'm saying that BN is generated by the following braids. And again, the proof of this, you would need some time. I mean, you could do a master course on braid groups, so you could spend hours. But the idea of the proof is quite natural. So you pick the braid you want to look at. So given B, geometric braid. You take a representative, so something isotopic. So you can find in its isotopic class a representative that is nice, like I said, so plus nice braid diagram, plus the crossings in the braid diagram are not for the same level T. So if you have a braid like this, another strand, here another strand, so what did I, up, up, up. So if here they appear at the same T, you're just allowed to move them a bit apart in your isotopic class. So this one you will get a bit downstairs. So you will move this strand here. And this one a bit upstairs maybe. So that now it's happening here and here instead of the same level. So this is possible to do. It requires a bit of geometry. And once you have such a representative, so red is better to see something. So let's see. No, this one was below, this one was above. I'm trying to redo them, but it really does not matter which one. And this one, is it at the same level? It is at the same level. Up. Up. And this one was underneath, and this one was underneath. I'm sure you can draw them better than me. So now the idea is just to slice your interval. So the first crossing is here. I should not have done this one. Okay. Let me do something terrible. So you're here. You're going to go very downstairs. Now your two are going to be very upstairs. And you're going to be a bit below, but not at the same level, so maybe much downstairs. And this one I did, this one I did, this one I did. What's left? Yes. Yes. Even downstairs. Even downstairs. Here. So now I will slice my interval 0, 1 so that I have only one crossing in between. And here we go. So T1, T2, T3, T4, T5. And so you see that here, what do I have? So 1, 2, 3, 4, 5. So here I have sigma 3 plus. Here I have sigma 1 plus. Here I have sigma 4 plus. Here, do I have only pluses? Probably. Sigma 2 plus. Sigma 1, 2, 3, 3 plus. Sigma 4 plus. You can do an example with minuses, not like mine. So then once you've sliced your interval, the braid that I just drew for you is nothing but this product. So let me change this one so that we have a minus at least. 1. So that you don't. It's an easy fix. So any braid you can now write as a product of these elements sigma I and sigma I minus 1. I minus, yes? Say it again because I couldn't hear. Yeah, right. Why? Because of this generic thing, you need enough space to have this crossing only happening. I mean, 0, 1 is compact, so you can't have this happening more. Why? Okay. Yeah, now it's obvious to me, but there must be like a good argument. I would also like to say that there are just a finite number of strings. That's not enough. If I have a better argument, I come back to you. Yeah, I need some striking argument that fixes that though. Other questions? Well. Yes. So, what time do we have? Yeah, I should finish soon. So, are you convinced that you can write these words of sigma I plus and sigma I minus instead of any of your braids? If yes, then it's easy to then figure out what should be, no, this one. Then it's easier to write what should be the inverse of your braid, because you can see that sigma I plus and sigma I minus are inverse for each other. And it's easy for just one crossing. Where is my red? So if I do this and then this is isotopic to just the two strands that are straight. And the same with the product the other way around. So here I have sigma I plus, sigma I minus. In other words, sigma I plus minus 1 is sigma I minus. And so now if I take a braid B and I write it in my monoid, as so a product, so sigma I1 plus minus 1, sigma I2 plus minus 1, sigma k plus minus. Then B minus 1, so I should write for you the class each time, is just so sigma ik, but now minus plus, sigma I2 minus plus, sigma I1 minus plus. But so you just have to check the isotopy for those, and then you know that you get an inverse for any braid. So you kind of break the proof into small pieces. So that's the nice feature of these generators. And now, so Bn is a group, and it is generated by, well, I can take sigma 1 plus sigma 2 plus sigma n plus. I don't need to take the minuses anymore because they're encoded in the group structure as inverse. So by those, or by the family with the minuses, if you prefer those. Doesn't matter. But these generators have a nice feature, and I will start with that again this afternoon. So these generators yeah, maybe for the break till later exercise. Look at sigma 1, sigma 4, say, and sigma 4, sigma 1, and say, yeah, sigma 2, sigma 3, sigma 2. So maybe we want 5 strands, so in B5. And sigma 3, sigma 2, sigma 3. So let's put pluses. But you can do the same with the minuses if you prefer. And yeah, I'll start from there in the afternoon. And we'll go away a bit from the topology into generators and relation for the Braid group, a bit of more abstract algebra. And then I'll go back to some topological stuff later on. Okay? Questions from now before we have the break? So I'll see you this afternoon.